And both the domain and the range have the weak start topology. The restriction map is a continuous map, then both the domain and range. So now, if I have a set K, which is a weakly compact in X star, then I can take the image of K, gamma of K. But continuous linear maps are automatically weakly continuous. That is one of the basic things in product space theory. So the continuous image of the compact set is a compact set. So gamma K is actually a weakly compact subset of Y star. So there is a very beautiful natural question that comes is that can weak compactness be determined by requiring the restriction image is weakly compact? Well, not for all Y, because then I can take Y is equal to X, but for a special class of proper subspaces Y containing X. Suppose on the other hand, you don't assume K is weakly compact, but you know that when you restrict it to Y star, it is a weakly compact set. And of course, you have to take proper subspaces, otherwise I will get anyway K to be weakly compact. So, is there a class of proper subspaces for which you can consider as a weakly compact set? So, this kind of a question becomes extremely interesting if X has an additional structure. Then I can take a proper subspace which has an additional structure, that kind of a thing. So, here is a nice theorem. In C-star algebras, there is a very beautiful theorem of Hermann Fischer, which says that weak compactness in dual of a C-star algebra is determined commutatively. In other words, if you take any commutative subalgebra B of A, and if you know that the restriction map K is relatively weakly compact in B star, then A is already weakly, K is already weak star subset of X star. This is from his mathematical paper, and he was a PhD student when he did his thing. And I was a postdoc in the same department, and the excitement was really palpable. Nobody expected that a compactness property can be actually commutatively determined in a C-star algebra. So here is the main theorem. So here is my notation. I would call W star is a one-Lyman algebra. That means W is the pre-dual of the one-Lyman algebra W star, and of course it has a unit E. And so here is something that I need to explain to come to my terminology. So note that when we are looking at objects like one-Lyman algebras and C-star algebras, particularly non-trivial ones, that is infinite dimensional spaces, they are automatically non-reflexive as Banach spaces. So what does the non-reflexivity mean? So I have a Banach space X, I have an X star and I have an X double star, and this is of course very canonical process in mathematics. When you do it a second time, then first object would naturally sit inside the object where you have repeated. No matter what branch of mathematics you do, somehow when you do an operation twice, you expect the earlier thing to be is part of the second time that you do. So this turns out to be a linear isometry. And if X is not reflexive, this is a into map. And also, there is another little bit I need. So in X star, we talked about weak star topology. And well, if you take any X belonging to X, the evaluation map, let's say X hat, whose value at any X star is equal to X star of X, is automatically a weak star continuous map. maybe I should write on the top. And conversely, if you have a map phi from x star, weak star to the complex plane, which is linear and continuous, then phi must look like a x hat for some x belonging to x. In other words, weak star continuous, the points of x are precisely the weak star continuous linear functionals on x star. This is again somehow a natural phenomena, because you somehow do the continuity. Weak star topology is already continuity against points of x, and then you want to do what are continuous functions here, you don't get very far. You come back to x. Points of x are precisely the weak star continuous functionals on x. So now I have my one-Neumann algebra. So W star then I am looking at the state space. That means I am looking at the second dual of the space W. So this is the one-Neumann algebra, that is the dual. And if I look at the E, and I am looking at the state space, SG is now on tau in the unit sphere of the space, which takes E to 1. All right. So naturally, since we are using one-Neumann algebra and C-star algebra theory, it does require a little bit of background material from this kind of spaces. So what happens is that when you look at this, but this is of course a weak star compact convex set, as we have already seen, but it turns out that the identity, for example, always, which is an element of W star, always attains its norm at a point of W. The identity always attains its norm at a point of W, so always have a W naught unit sphere of W, such that. So, if I look at this element W naught and consider it as an element of W second dual, that's where I am using the embedding, this element that comes out of the C-star one-Neumann algebra theory is actually a weak star continuous state here. So W naught in S of V is a weak star continuous state. This entire thing makes sense only because we have one-Neumann algebras. So W star is a weak star continuous space. So now what I want to say is that suppose I take them out as a separate set. Suppose S prime is the collection of all weak star continuous states in S of E. It is guaranteed because the theory tells me that the identity itself would attain its norm. So there is consequently a weak star continuous state. So I collect them all. Suppose that you can decide is a weakly compact set of omega, then A nest must be necessarily finite dimensional. And the second theorem is that if a C-star algebra, if a unital C-star algebra, if the state space is weakly compact, then the algebra must be finite dimensional. So in other words, if you look at Hermann's theorem, what I am trying to say is that if you look at a similar thing of weakly compactness in the C-star algebra, and if you know that some good sets like the state space are weakly compact, can only happen when the algebra is just finite dimensional C-star algebra. This analysis that I have in mind is quite natural, and people are very often ask me when I look at these pictures, X and write X star and write X double star, they would say, oh, this is craziness, why do you want to do this kind of a thing? But if you look at a C star algebra, its second dual is again a C star algebra. Its second dual is a C star algebra with identity, it's a one-ion algebra and everything. And that process continues. The beauty of this structure theory is that this process continues. You can again take another second dual of whatever you have taken, and that would again be a C star algebra. And it is known in this theory that when you do this process, you have getting increasingly complicated objects. For example, if you look at compact operators on a Hilbert space, then this is something that most of you know, is that if the dual is the trace class operators, and if the second dual is B of H. And nature is blessed us so much that this canonical identification of a Banach space in its bidual is just the inclusion map of compact operators in the space of bounded operators. So one of the prime examples why this canonical embedding and this kind of higher order geometry is an interesting thing. All right, so this is the one-ion algebra. So this is the reason why one is interested in. And for me, I have been doing this higher order geometry for a long time. Given that when you take the higher duals, the structure is getting more complicated, what would be interesting is to decide the entire thing by only looking at X, X star and X double star. Suppose, yeah, please.
So what is an A? I mean, you're using W, right? A star.
Sorry, this is a typo. W is fine. Yeah, W, thank you. Right. So generally thing is that, you see, this is the kind of looking at through a telescope. I look at X and I look at X double star and I look at beyond. But suppose somewhere between X and X double star, which is the most popular objects, for most Banach spaces you can figure out what is X star is, and one of the excitements is that for all popular function spaces, the dual can be determined, and bonus is that the dual can be again a function space, that kind of a thing. But the second dual would most invariably go into a very complicated object. So if you could decide matters between X and X double star and see how these things would go, then you are in good shape. So that is one of the philosophical reasons why I consider this kind of a question. So since I have a younger audience, I give you another philosophical reason. Compactness is something which is an individual property of a set. In other words, every net in the set converges to a point of the set. So compactness does not depend on compactness where. You don't have to ask me with respect to what. So my assumption that this is something is weakly compact in X, it would automatically be weakly compact in X double star, because compactness is a relative property of X. So when I take it into K, of course every net will have weak topology, as I said, of a subspace is same as the restricted weak topology. So if something is compact here, it is compact here, or if something is compact here, then of course it is compact in the third dual. Right. So that is the reason why compactness seems to be an appropriate condition to put, because then I am not worried about where is this thing compact kind of thing. Alright. So that is the theorem. So here is the proof. So this is where this entire picture comes into picture. So consider the canonical embedding of the pre-dual of the one-ion algebra in double star. Now there is something very nice happens. The collection of all weakly continuous states that have weak star continuous states that I have picked up from SRP, not only that is a reasonable collection, it can be proved as a part of the one-dimensional algebra theory, is that this weak star continuous states in SRP would actually form a weak star dense set in SRP. So now notice that the weak topology of a space is same as the restricted weak topology. That's what I have been saying here. So this set S prime, which I am assuming now to be a weakly compact set, continues to be a weakly compact set in W star. But we have already noticed that if you have a weakly compact set, then on that the weak star topology is same as the weak topology. But by standard theorems in one-dimensional algebra theory, I know that it's a weak star dense set. But this is also weakly compact, so that means it must be the entire state space. Okay? So the set of all weak star continuous states becoming the entire state space is a very remarkable feature. So I just want to go back to what I said in X and X double star. So we have X canonically embedded in X double star, and reflexivity means that X double star is same as X, or to say that every weak star continuous linear functional from X double star comes from an element of X star. That is same as saying that X is a reflexive space. So what I am saying is that in the case of C star algebra, I have that all the states are automatically weak star continuous states in the case of a one-dimensional algebra. Now it is quite easy to see that continuous way. Okay. Right. So there we are here. S prime is S prime. But remember, so this is where my starting motivation of probability measures comes in. We have already seen in the case of probability measures, the state space span these entire measures. Similarly, this is again standard property of C star algebra. If you look at the span of state space, if you look at the span of state space, you get W double star. And those of you who do one-dimensional algebra also know that if I look at these states which are weak star continuous, they would always span the pre-dual of the one-dimensional algebra. So span of SC is W double star, span of S prime is W, but we say that SC is same as SW star, so W is a reflexive one-dimensional algebra, and reflexive one-dimensional algebras are just finite dimensional. For example, any non-reflexive one-dimensional algebra contains an isometric copy of L infinity, so it can't. So reflexive algebras must necessarily be a finite dimensional. So this automatically gives me the result for C star algebras. Namely, if I now start with a C star algebra, A unital, then I look at A double star, that's a one-dimensional algebra, and as I said, the nicest thing in A star algebra theory is that the bidual actually has a multiplication, it becomes a C star algebra, and the canonical embedding of a Banach space in its second dual that I have described before would say that this natural embedding is actually a star homomorphism between star isometry between these spaces. So identity then continues to be the identity of the second dual. So now I can consider S. My assumption, this is S of E. So I have the state space S of E. So now let S of E to be all those, so this is in the second dual, so all those star in the unit sphere of the third dual, such that of E is in. And this is now the state space of this one-ion algebra S of E. So A is the C-star algebra with the unit, and A double star is the one-ion algebra. E is also actually unit. And now, if I look at this state space with respect to this, and if I ask myself, what are the weak star continuous states in here? They will be precisely the things in the state space here, because we showed that if you have something in weak star continuous, then it must come from the first dual. So this would automatically come to S of E. So that if you start with a unital C-star algebra, you take the unit as an element in the second dual, and then you formulate the state space there. Then in that state space, the weak star continuous states are precisely the ones you have started at the bottom level. Okay. My assumption now is that this is a compact set. Okay. So, all right, note that this is the C-star algebra. So, the assumption on the compactness of S of E, like the way exactly I did here, S of E implies that A is finite. I just repeat my original picture. My original picture is for a one-ion algebra, but I know that my original picture repeats itself even if I look at a C-star algebra and look at the corresponding enveloping one-ion algebra. My original picture just repeats itself. So I just repeat my previous proof. I immediately see that S of E, A must be a finite dimensional C-star algebra. So this is for me a nice combination of basic C-star algebra theory. Of course, you don't see it from the point of view of a Banach space person, but this is just very routinely used C-star algebra, one-ion algebra theory. But you put it in the perspective of Banach spaces, and you ask the question, when is the set of states a weakly compact set, then it will turn out to be a finite dimensional case. So that finishes the proof of the theorem. So now, of course, one should go a little deeper into this question. So this is again something only a hardcore Banach space theory people would worry about. So let W star will be a one-ion algebra. That means I am looking at a one-ion algebra which is a second dual of a Banach space. Right? So these are one-ion algebras which appear as the second dual. Then what is very nice about one-ion algebra theory is that there are several Banach spaces. It is known that there is uncountable collection of non-isometric Banach spaces in the infinite dimensional case, okay? Not finite dimensional case and reflexive. So in the infinite dimensional one-ion algebra, which if it is a second dual, then there are uncountably many non-isometric Banach spaces whose second duals agree with this one-ion algebra, which is a second dual. In other words, your popular picture of the second dual of compact operators is the bounded operators on the Hilbert space, actually has several answers if you ask Banach spaces X whose second dual is P of H. There are uncountably many non-isometric Banach spaces whose second dual is same as the bounded operators on a Hilbert space. So there is, of course, this is where the famous Grothendieck picture would come. So if I start with a one-ion algebra, V, W, I have the W, which is the equal of W star. So when I look at a one-ion algebra and I look at the dual of a one-Neumann algebra and ask for the weak star topology, there is a beautiful theorem of Grothendieck and Dixmuir which says that it is a uniquely determined object. For a one-Neumann algebra, the pre-dual is isometrically one and only one Banach space. There is a unique Banach space whose dual is a one-Neumann algebra. So if I write down a one-Neumann algebra and say, look at things which are continuous in the weak star topology, you don't have to ask me weak star topology where. There is just only one weak star topology. There is only one Banach. But if you now look at a one-Neumann algebra, which is a second dual, then I already know that there is uncomfortable choices of what I could call as weak star topology in this situation. So the question is that keeping the previous notation, so W star is a one-Neumann algebra which is the second dual. In general, there can be several spaces whose second duals agree with this, but keeping the previous notation, consider that there is a weak star closed set in some weak star topology which gives you these states S prime. Then can you determine the structure of the one-Neumann algebra? So that is the kind of a question that I am interested in. I have recently partially solved it in a certain class of Banach spaces, but in general it seems to be too huge to be able to answer this kind of a questions. Can you find one Banach space X so that with respect to that weak star topology, things actually are nice kind of thing. So I will leave it with that question and go to the non-unital case. I have 10 minutes, right? Yeah, good. There. So just let me quickly go through the non-unital case. So this is the picture. So non-commutative case with the radar-Nikodem property pre-dual. So you have, this is what I am saying. So theorem of Dixmuir's projection, this is called. Dixmuir showed that the dual of bounded operators on Hilbert space is really compact operators, that is dual, that is trace class operators, and it is an L1 direct sum of the annihilator of the space of compact operators. Using this, one can show that if you now look at the unit sphere of trace class operators, and remember my state spaces are inside the unit sphere, weak star and weak topologies are the same. So this is the reason why, in general, I have insisted that my states become a weakly compact set, because in this classical case, the weak star and weak topologies are the same. And that the weak star and weak topologies are same is a nice property, that's a hereditary property. And duals of such spaces, that means if X is such that on the unit sphere of X star, weak star and weak topologies agree, then X star will have very nice metal theoretic thing called radar-Nikodem property. So in my mind again, these are all very interrelated. I have started my talk with the motivation of Rie's representation theorem. Then I also know that this is intimately related to, in the vector valued case, solving the radar-Nikodem theorem. You have a vector valued measure and you have a positive measure that this is absolutely continuous with respect to that, then is there a radar-Nikodem derivative, and this is what one has to assume. Somehow this entire thing is related to these quantities. And so since not many people know, let me just go through these guys. So the CCR algebras, that is called compact algebras, they are precisely C-star algebras of K of H, and C-star algebra has this property then because this is a hereditary property for K of H, have the property that weak star and weak topologies coincide. So consequently, for any A belonging to A of a C-star algebra, the corresponding state space is a weakly compact set. So what we have generally proved is that my state theorem is roughly to say that to see the converse, you just have to know for the identity map. You don't need it for all A. For the identity, if you know that S of T is the weakly compact set, it will automatically determine the structure. All right. And so this is a very beautiful result of Chu, which says that if you have a one-Neumann algebra whose pre-dual has the radon-Nikodym property, then A is automatically the enveloping one-line algebra of a CCR algebra. So this is again a very beautiful connection with whatever it is that I am doing, and this comes from a result of Chu one-line algebras, which are second dual spaces. This is proceedings 91, and this is the structure of one-line algebras whose pre-dual has the radon-Nikodym property. Yeah. Since Kalyan is here, I just wanted to mention that the Chu and I have the same mentor. We both worked with Professor A.J. Ellis, who visited ISI in 80s and gave a series of lectures and started me off in this theory. So, all right. So let me just now show the non-theoretical case. I don't know, for some reason I'm not getting that slide. So maybe I'll just write it on the board. Yeah, this is it. A is the C-star algebra, and in the non-unital case, then I cannot have identity. So I'll assume that every non-negative unit vector is A in the unit sphere, the corresponding state space is weakly compact, then the C-star algebra is a CCR algebra. So in the unital case, we get them to be finite dimensional by assuming that S of E is a weakly compact set. In the non-unital case, if you assume that the state spaces corresponding to non-negative unit vectors form a weakly compact set, then A is a CCR algebra. Almost done? 4 minutes, okay, good. Yeah, so the thing is, of course, the path is very clear. One somehow solves the commutative case. So I do this by when A is C0 of omega, where omega is a locally compact space, and then show that that means the locally compact space is discrete. And then, of course, there is a very beautiful result which allows me to put them together. Okay. So there is this result that use is due to Contreras, Paya, and this is Werner. They showed that if you have their paper is called C-star algebras, which are I rings in JMA 1996. They showed their results would actually allow me to show that the restrictions I have put on my C-star algebra would automatically imply that the C-star algebra is algebraically, isometrically C0 direct sum of K of compact operators on a Hilbert space, which of course is a CCR algebra. So basic picture, somehow what I drew on the board of compact operators, dual being trace class and the second dual being BFA, that picture is really extraordinarily beautiful picture. A lot can be read from the geometry of it. And then you try to imitate that geometry elsewhere and you realize that you are just back to the original picture. So my thing is really C0 direct sums of compact operators on the Hilbert space. So I think I will leave it here. Thank you.
Thank you, TSS. So what do you mean by C0 direct sum?
So that means that you consider it as a functions which vanish at infinity, valued in the union of the Hilbert. So this is the standard procedure. There is the structure theorem, you can find it in Arvison's book, which says that a closed subalgebra of C-star subalgebras of K of H are precisely those which are C0 direct sums of a family of compact operators on a Hilbert space. So, for example, again, Banach space theories would be interesting questions. So, I have, for example, looked at questions which would automatically tell me some kind of an algebra or a geometry saying that these K of H alphas are actually should be finite dimensional. When can I say what kind of CCR algebras are automatic, of course, would be. And in particular, this includes the space C0 on a discrete set. And for that, the answer is simple. If you have a CCR algebra which is commutative, then it is C0 on a discrete space. That is known. But in general, again, one can classify when can you say that all the H alphas should be one finite dimensional or all the H alpha should be one dimensional and things like that. But that is just a small corollaries to this kind of a structure theorem. Yeah.
Any other questions or comments?
So this is, these are simply, compact these are the algebras of compact operators on a Hilbert space. Completely continuous. Yeah, no. Harbison uses this notation. Earlier one, yeah. Like that, Harbison, for example, starts as a GCR and CCR algebra. Completely continuous, I suppose, ranges. Right. Earlier. Right. In fact, what I will also probably continue to use completely continuous before switching over to the compact operator notation. Thank you.
Thank you, sir. I would like to invite our chair to present a token of appreciation to our speaker. Let's move on to the next session. To introduce our next speaker, who is Professor Rajaram Bhatt, I invite the chair, Professor Fumihiko Nakano.
contributions to quantum stochastic high-class and quantum dynamical semigroups, earning the prestigious Shanti-Saraka Prize in 2007. It's that.
Can you hear me? Yeah, as I said, I'm very happy to be in Kerala. I come twice or thrice in a year, typically. So, okay, so what I'll talk about, before that, I would like to thank the organizers, okay, and for everything here, especially Professor Narayan, and we are missing Professor Nambudri, so anyway, when we come here, I meet him. So, anyway, so I also want to thank JC Bose Fellowship, and this work is based on a joint work with Keshav Bakshi in IIT Kanpur. The archive version is there and it will appear in IMR. Okay. So what I will talk about is really finite dimensional thing. There are many words, fundamental algebra, sister algebras, etc. But nothing much. It's just finite dimensional matrices is what is there, and unitary orthonormal basis. I'll give some necessary conditions, constructions, and applications. So let me come to straight away. Okay. So we consider CN as your unitary sister algebra, but also as a Hilbert space. So that means you think of the diagonal matrices. So you think of Cn as just the diagonal matrices. So then, okay, like x1, x2, xn, like this. Okay. So then it has both the structures. Means the sister center you can multiply, and also you have an inner product. So the inner product here, the natural inner product. I have the antilinear in the first variable. It's just a matter of convention. You can put it in the second thing, and I have divided by n. So that the identity here has unit norm. That's all. Thing is that what we would like to have is that these two also the want to look basis which consists of unitaries, okay, not just arbitrary basis. So I want to have this xj's to have modulus 1. Okay. So that means suppose I have an orthonormal basis of Cn. Now, so you see, we are mixing the Hilbert space structure as well as the algebra structure. So you want unitaries forming an orthonormal basis. So I have divided by n for that. Okay, so now suppose I have an orthonormal basis. So you put them as column vectors. And what you get then is a unitary matrix because you have n many vectors. If you have full orthonormal basis of unitaries, then finally, if you write them all together, what you get is an n cross n matrix which say unitary having the entries all should have modulus 1 divided by the number 1 by root. So you can think of real things here, okay? And conversely, if you have such a thing, then you will get orthonormal basis like this. So the simplest example, like this one, like this is orthonormal. With all the entries have the same modulus 1. Okay? And if you just divide by root 2, you will get a unitary, like that. So these things like with this, these are known as Hadamard matrices, like 1, 1, 1 minus 1. And you can have the similar thing with 4 by 4 if I want. So then it will be like this. you will have to tensor with the same thing. What you get is a matrix like this. So you repeat the same thing. Then you take the minus of this. Okay. So this will be a 4 by 4 unitary. When you just divide, you have to divide by this. But otherwise it's orthogonal. The rows are orthogonal, the columns are orthogonal. All the entries are equal to 1. This will be 1 by 2, right? This will be plus 1. Right? The minus of this, you take a tensor. Yeah, it will be orthogonal. Okay. So this is we call this a real Hadamard matrix. They are called Hadamard matrices. You can take tensor the same thing, then you will get something of the to the power n. So the rows or columns are orthogonal to each other. All the entries are 1 or minus 1. So in the real case. So what we know is that you can write if n is bigger than 2, then the order has to be a multiple of 4. Okay? That can be proved easily, not much difficulty. You can prove that if you have a real Hadamard matrix of order n with n bigger than 2, n equal to 2 you have 1, n equal to 3 is not possible, and bigger than that it has to be a multiple of 4, and it's a big conjecture as to it is possible to construct real Hadamard matrices for all multiples of 4. Okay, it's an open problem, nobody knows the answer. But in the complex case, things are much simpler. You can get a unitary for every n. Okay, and here is the explicit, we have written a unitary. Okay, so you have to, so the jkth entry is the exponential 2 pi ijk by n. So, and this is as a name, it's called the finite Fourier unitary. Okay, so it's like Fourier transform, but infinite, it's also called discrete unitary, discrete Fourier transform. Okay, so this exists for every, and it appears in many different fields. Okay, so you can see it, and so this was a basis for Cn. Okay, Cn considered as also unitaries. Now I look at the full matrix algebra, n cross n complex matrices, and I have the inner product, standard inner product, trace of x comma y is trace x star y. This is nothing but the, okay, you just think of x as some x11, etc., x and n. The inner product is summation xij bar yij, that kind of thing. Standard inner product. You can also write it as trace x star y. Again, I have divided by 1 n so that the identity in the norm gives you 1. Okay, and more generally, I can multiply by a density matrix, that is a positive matrix of trace 1, and consider that kind of inner product. Okay, so x comma y, the inner product given by a density matrix already. By a density matrix, I just mean a positive matrix of trace 1. You write trace of row x star y. And then row should be positive and trace should be 1. So here, this is the special case, identity by n, which is positive with trace 1. So this gives you an inner product on n cross n matrices, and then we ask for an orthonormal basis consisting of unitaries. All the basis entries should be unitaries, and you want to have an orthonormal basis. Okay, and there is possible, known as Weyl unitaries. So you consider standard orthonormal basis on Cn. So I start from 0, convenience, and I have written 2 unitaries, u and v. So the u is the diagonal operator. Okay, the diagonal where you multiply by the powers of the roots of unity. Okay, so I will have 1 omega square, that kind of thing, and then there is powers. Okay, so that is the u. And the V is just a cyclic permutation. We have put the one should come back. Okay, be something like this. The V will be 0, 1, 1, 1, and then here 1. Okay. So I have written 2 unitaries, u and v. Now you take so u is diagonal and v is a cyclic permutation, and you take possible of u and v. U to the power of j, v to the power of k, you vary between 0 to n minus 1. This collection forms a basis for the collection of n-cosine matrices. The vector space of n-cosine matrices, a basis consisting of completely unitaries. See, normally for n-cosine matrices, you take the matrix units as the ijth entry is 1, the rest is 0 as the basis. But this is a much better basis. With the basis, all the entries are unitaries. Okay? So these are known as Weyl unitaries. There are some infinite dimension analogs also, but I will not go into that. So we will do today only matrix theory. So, okay. So in all the cases, there is an inner product. So you get a Hilbert space, and where you have you get a means from the inner product you get a Hilbert space, and we are talking about the basis for that. Okay. So recently, these people, Crane, Krebs, and Pereira, they got a basis for this kind of things. Okay, unitary basis. So I just gave you the basis for two bases, one for Cn, unitary basis for Cn, the initial one, okay, and then for Mn. Now this is the general one, like you want to have say Mn1 direct sum Mn2 like this. So all sort of block matrices like this, x1, x, yeah. 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 Yeah, I'll come to that. I'll come to that. Okay. So this one was, it's a good question. It's a natural question. Special choice was made for rho as identity by n. Okay. Now generalizing this. Okay. Another thing, this one. Generalizing this, these people, Crane, Krebs, and Pereira, they got the similar kind of unitary orthonormal basis for which algebra? Algebra like this, M, N0, N1, direct sum of matrix algebra, right? So these are diagonal blocks of matrices of different sizes, okay? There also, for that space also, they got unitary orthonormal basis, but where for a suitable state field, okay? That rho, this kind of density matrix was fixed, like something with J chose, okay? Not arbitrary one. So like here we had chosen identity by n. Similar thing, they had some formula for that. I'll come to that. But this came because of some applications in subtractive theory. Keshav and others had made some conjecture, and these people solved it and got the answer. Okay. So our main goal is to extend this to a little more. Okay. So, and this too has applications in subtractive theory of phenomena algebras. Okay. So what is the setup we'll work with is this kind of set, B contained in A with the map E. Okay. So A and B are phenomena algebras, but as I said here, it will be only matrix algebras, direct sum of matrix. Like when I take Mn0 direct sum, etc. Mnk, that means block of matrices, okay? And D is a subalgebra of A, and E, so the setup would be always like this kind of triple, one big algebra, another subalgebra, and a map from the bigger to smaller, called conditional expectation map. The simplest thing to think of is n-cosine matrices and the diagonals, okay? So similar thing one can have the bigger things, okay? So that is the setup. Okay, so always there will be a sub-algebra and a bigger algebra, and and from the bigger to the smaller, I will have a map E called the conditional expectation map. So the conditional expectation map is typically like this, like the bigger one. Suppose it is something like this. Okay, so all possible things. Like this is the bigger algebra, say. Then you may map it to first to the of the diagonal blocks, say x11, x22, like this. Okay. make everything at 0, so just take the diagonal things. Then you take sort of the average of the things, like this one plus this one by 2, like this kind of thing, okay? So that is a kind of map, the conditional expectation map. Okay, so it's a mapping from the bigger to the smaller. On the smaller space, it is identity. Okay, so it is like taking the block matrices and look at the diagonal things. Okay, so
So the final one will be 2 cross 2 like this, right? That is not significant 2 cross 2 like.
no, so see, there are various versions possible. So I will have a subalgebra B inside a bigger algebra. And the conditional expectation map will be a map from the bigger to the smaller. On the smaller one, it will be just the identity map. Okay? So one possibility is that you have this kind of things and you just take this block. Okay? So then that will be a conditional expectation map. And then you may have further, you may take the average of this and this here. Then you apply it again, you get the same thing. Okay? So there are other possibilities. But always a map from the bigger algebra to the smaller algebra. On the smaller algebra, it is just the identity map.
The matrix is
Yeah.
given the order of projection
So there are multiple choices. So one way, like just from matrices, you just map it to the diagonal. That is a conditional expectation map, where you just take the diagonal algebra as your subalgebra. Okay, when the diagonal algebra is subalgebra, you just map the whole matrix, just take the diagonal. If your subalgebra is just the subalgebra of complex numbers, then you take the whole matrix and then take the trace. Trace times identity. Okay? So it depends upon what is the subalgebra. If subalgebra just consists of the diagonal, the complex numbers, the complex numbers you will always identify as complex numbers times identity, as in the bigger thing. So you map the matrix to the trace times identity. That is a conditional expectation map. So it's a map from the bigger to the smaller. On the smaller space is identity. Okay? And the bigger to smaller, the map should have certain properties which I will not go into. Okay? It should be unitary, completely positive and all that, but okay? So once you have a setup like this, a smaller one and a bigger one, and you have a map from the bigger to the smaller. Okay? So typical example, you can think of like n cross n matrices and the diagonals. That is one possibility. Or n cross n matrices and this is the complex numbers. Complex numbers times identity. So that is the scalar. So whichever way, you take a subalgebra B inside a bigger one, and then a basis for the bigger one. So all the times like this A, B, all we are taking finite dimensional things now. Okay. So here you want to have a basis for the bigger space. So W0, W etc. WD minus 1. It's a unitary basis, means they all should be unitaries, and they should be orthonormal, means the inner product between Wj and Wk should be identity of 0. So that is orthonormal. And this equation, what it is telling is that every element in the bigger space can be expanded using the basis. Okay? So the basis elements are right? These all we would like them to be unitaries, and every vector, every element of A can be written and expanded using the basis. Okay, so this is the formula. It is the usual formula you have in the vector space, in the Hilbert space. You have a vector x, then you can expand it using the inner product times the basis vector. I have just written it on this side instead of this, because here it matters whether you write on the left or the right, because they are themselves matrices. Okay. So this is the setup. B inside A is the bigger algebra, B is the smaller algebra, and for the bigger algebra you want to have a basis, unitary basis, all the elements you want them to be unitaries, and the coefficients, when you have the basis, the coefficients come from A, the smaller algebra. Okay? If the smaller algebra is just the complex numbers, you have the usual notion of the usual Hilbert space inner product. Okay? These are called Hilbert system modules now. So that would be a left basis. Okay, you can choose either one. Okay. So what this is telling you is that you have these wj's, we want them to be unitaries, and every vector x can be expanded using the wj's and the coefficients coming from the smaller thing. When the smaller thing is complex numbers, you have the usual notion of the basis. So it is an extension of the usual notion of a basis, Hilbert means orthonormal basis. Okay. So we want the orthonormal basis also to be consisting of unitaries here. That is the only difference. Normally when you have a Hilbert space, you just talk about orthonormal basis because there is no product on the Hilbert space. Now our Hilbert space consists of matrices. So you can multiply, so you can talk about the unitaries there. So you want to have a basis consisting of unitaries. Okay. So like this the first question was this diagonals which I considered, and the C inside Cn. Okay, then we had Hilbert space consisting of just diagonal matrices, and there the question came of Hadamard matrices. The second one was the Weyl unitaries. So what I have given are the examples for the two cases, C inside Cn and C inside Mn. So both the time it was Hilbert spaces. The orthonormal consists of just for the diagonals, it corresponds to Hadamard matrices. For Mn, it corresponds to this example idea, the Weyl unitaries. Okay? So the question is, when you have a subalgebra like this in the figure, when can I get a unitary basis? This basis which I gave, when does it exist? When can we have this kind of Stinner-Popper basis consisting of unitaries? Okay? And without unitaries, it is always possible, but with unitaries, can you get the basis? Okay? So the thing is that this looks rather peculiar question. Why do you want to mix the two things, basis and unitaries? So somehow this came up in the subfactor theory. So what they have in subfactor theory is they want to classify some big phenomenon algebras, one sitting in another, they want to classify them. So they get some invariants, and finally it comes down to matrices, matrix algebras. And many conclusions can be drawn if you have a unitary orthonormal basis like this. It can be used to derive results for subfactors. So these questions are in finite dimension, but the conclusions, because of this, you can have many consequences for the subfactors. Okay? So that is the idea.
Also there are implications in quantum mechanics because if you want to implement a particular kind of operator,
Yeah.
can you do it using unitary?
Yeah, sure.
You can expand them using unitary.
Yeah, but I don't know the quantum things when there is one inside another. But there are a lot of, like I have to be inside A, that kind of situation. But here, definitely for subfactor theory, it has many applications. Okay, so this is the setting. Okay, you have the bigger algebra. As I said, I restrict to matrices, direct sum of matrix algebra. Okay, B is sitting inside that. So, typical example. Suppose I take my B as say M2 direct sum C. Okay, C is just M1, and then any element would look like this. Okay, any element in B would look like this. This is a 2 by 2 matrix, and this is some vector. And then you embed it, say like this. Okay, maybe I put one more. Okay. So this could be an embedding. So here I have this 2 by 2, so I will need 4 and 5. So A would be say M5, or direct sum M2. Okay. So this, all the things here will belong to the algebra M3 inside A. So how are they related? So for any such embedding, you get a matrix called the inclusion matrix. So Aij describes the number of copies of the j summand mmj in the ith one. Like for this embedding, for instance, this one gets embedded twice here, and the 0 times this, and then here like this. Okay. So this is the embedding, the number of times. Okay. So this I can also draw like this. Okay. So this one, okay, this is embedded twice in the first copy, okay, and 0 times in the second one. Whereas the second one is embedded once here and twice here, right? This is twice, like this. This is called Bartelli diagram, okay, Bartelli diagram. So it tells you how the smaller one is embedded in the bigger one. So Aij describes you the embedding, okay. The j summand here appears Aij times in the Ni, okay. So I'm going very slowly. So these parameters then, since the whole thing has to match up, you will get the matrix A times M equal to N. Okay. So this is just adding the dimensions. That here you see this M5, you have to exact 2 copies of this and 1 copy of this together should give you 5. So like that, the matrix multiplication. This is called the inclusion matrix A. Okay. So okay. So whenever you have an embedding, unitary embedding of B inside A, this equation would always be satisfied. Okay. The A is called the inclusion matrix. It just tells you how many copies of Mj is there in how many copies of the ith summand. Okay. So Aij is write it here once more. The Aij is the number of times the jth copy appears in the ith summand. Okay. So B is inside A. Okay. So that is there, and we also need the states on the algebra. Okay, so if I have A as a direct sum of this, okay, like this M0 direct sum M1 like this, I can have the trace on each one, okay, and then take converse combinations. So that would give a trace on the full. Okay, so that is what we have done. A faithful tracial state on A is each one you put trace and then multiply by a constant, you take a converse combination. And I have divided by summation Pi and I so that the trace of the state on the identity gives you 1. That's all. So any trace on the biggest algebra looks like this. Okay? And so these coefficients P is as a trace vector we will call, and it's a fact that whenever I have a setting like this, okay, B contained in A, and you have you put a state here on the A, then there is a conditional expectation map. There is a way of going from A to B. So I will not spend more time on that. Okay, and let me. Okay, I don't know how much time I have. Yeah. Okay. So let me also skip this. Let me go here straight away. Okay. So what this Crane and all did is the special case when you have complex numbers inside the bigger algebra A. Then you they got a special state. Okay, where you got the unitary orthonormal basis. He asked why you took I by n, can we do it for any row? But no, they did it for a special one, and the state they chose was this one. Okay, so this is the case. So I said for each one you take a trace, okay, and then take a sort of converse combination. Okay, what should be the coefficients, the pj's? The pi's themselves are ni's. Okay, it is not 1 by n. So ni times trace xi. It is with respect to this state, they got unitary orthonormal basis for one specific state. Okay, so okay, let me go with this. So what we want to prove here is that that was not accidental. Okay, it is the only state where which you can get an unitary autonomous basis. Okay, so in fact, so for Mn, you see it was the trace divided by n. Similarly for this one, so direct sum of Ni, the only state where you can get a unitary autonomous basis is the PIs, the coefficient you want to have in the convex combination. For the dimension Ni, it is Ni. It is somewhat strange because you don't have saying that you put the equal weight. The weight should depend upon the dimension. And if you remember, this happens in group representations. Irreducible groups, if you try to classify irreducible group, finite groups, the representations with Ni will come with multiplicity Ni. That's the same kind of thing happening. For Mni, the coefficient you need is Ni. So the dimension becomes summation Ni squared. Okay. So this will be the basis, the dimension of the unitary autonomous basis. Okay. Summation Ni squared. Okay. So I would ask, so C is, well, that is see, each dimension of Mni is Ni squared. So since C is inside this dimension of the whole thing will be summation Ni squared. Now this, okay, I will go quickly as to why this is happening. The unitary, the E has to be this specific one. And how do we prove that? We look at, okay, we start with arbitrary state, trace rho x. Then trace rho x, the rho will break up into rho i's on each Mni. And then you apply the spectral theorem for rho I. You get each rho I, you have its spectral decomposition. Okay, so this is the coefficient. This is just the spectral decomposition of rho I. So then you have orthonormal basis for the eigenvectors for each rho I. So put them together. So if you put them together, everything, what you get is, okay, so this is the, what I have assumed here, Wj's form an orthonormal basis. So you break it up in this and write in this basis, okay? And then if you see the orthonormality condition, trace rho Wj star Wk should be delta Jt. So just you expand it, rho I, okay? I write it using the basis, okay, because I have the, yes? Okay, you expand using the basis. And then what happens, you write it more explicitly, what you see is that when you have a complete orthonormal basis, you have the columns forming orthonormal thing, right? So then the rows also will be automatically orthonormal. If the columns are orthonormal, the rows also will become orthonormal. And that is what we use. So once you write this, okay, you expand the row into this using the spectral theorem and write this as a unitary thing, and you get a big unitary by putting all these orthonormals together. And then you see the row, just as columns, the rows also should be orthonormal. And that immediately tells you that this state conditional expectation could not have been anything else but all these Ni's. Okay? So that is the way. Okay? And next, what we do, if I have two unitary orthonormal bases, like A1 inside A0, I think there is some mismatch. Okay? It should be yeah, no, it is okay. It's okay. A2 contained in A1 is contained, so I'm going backwards. Backwards. So you can, if you have, what this is telling you is that if you have systems like this, like the previous time, suppose you have unitary orthonormal basis for one and another unitary orthonormal basis for this, you can multiply them and get the unitary orthonormal basis for the composed thing. Okay? And that is direct. You just multiply it out. If the composing two conditional expectation map is E1 and E0, you get a conditional expectation map. And that way you can see that, why I am doing this? See the, I want to look at this case, okay? The general case, where I have B inside A and I want to have a unitary orthonormal basis for that. Now, so I want to have an unitary orthonormal basis for that, and I want to know for which conditional expectation map E there is an orthonormal basis. So what we did is we put C inside this, okay, just complex numbers. Now if I look at this C and A, then I can apply the previous thing which tells from the that there is an orthonormal basis with a specific conditional expectation map. Okay, the previous result, as I said, those set by Gray et al., that was for the C inside the bigger algebra. For that, there is always an orthonormal basis for a specific state where the multiplicities are ni. Okay, so for this I can get an orthonormal basis. Okay, so if there is an orthonormal basis here, then I know this one also has a basis. So then I can extend, and then I can conclude that what will be the conditional expectation here. Okay, so that gives you the information about E. Okay. So the final conclusion is that this one, the conditional expectation has to be that one which with the dimension vectors, ni's. Okay. Just combining the two results. One case I know that there is a basis and the dimension has to be ni. Put them together and you have it for general one. So other main result we put here is that, so we want to do, first want to know when can we get unitary orthonormal basis, then construct them, okay, whenever it's feasible. So to when we can get, the first question was what sort of E should be there. So that was answered in the previous way, saying that there is a specific choice where you can get, and nothing else is possible. And other condition one gets here is that this one, whenever you have the second condition, what we get is this. Suppose this admits unitary orthonormal with the D unitaries, then the dimension vectors, so these are just the M and N were the dimension vectors, like A was MM0, etc. B was N0, etc. B was MM0, like this. These dimension vectors, they have a relationship. So the dimension vector becomes an eigenvector for A transpose. Okay, that is a necessary condition. So that means if you put the two things together, these dimension vectors have to be eigenvectors for A transpose A and A transpose. Okay, and D being the number of basis elements in the unitary orthonormal basis. Okay, so that means these are eigenvectors with non-negative entries. Okay, in fact strictly positive entries. So these are something called Ferrand-Frobenius eigenvectors. For matrices with non-negative entries, okay, there are things called Ferrand-Frobenius eigenvectors. So this is how to be Ferrand-Frobenius eigenvectors. So again, this I will skip the proof. Okay, so this is the second condition we get. So then let me skip that proof. Okay. So corollary of that is that when I have B like this kind of thing, in general you don't have unitary orthonormal basis B contained in A. Some specific conditions have to be satisfied. The conditional expectation is sort of determined by what are called these Ferrand-Frobenius eigenvectors, and the inclusion also is very specific in the sense that you have these dimension vectors have to be eigenvectors of A transpose A and A transpose. Okay, so these are the two conditions we get. Okay. So as I said, this a similar thing happens in group theory. So one of the corollaries what you get here is that the dimensions, if I have a unitary orthonormal basis, the sum of squares have to be related. Okay, sum of squares of this dimension coefficients for A and B are related by this kind of equation. Okay, so the sum of squares comes like from the group theory. Okay, and there is a direct computation to see that. Okay, So what we are doing is that we are doing conditional expectation. So see, suppose I have some, say, M5, okay, and then here, from here, when I do I have big blocks, and then you first restrict it to the blocks here, like this, arbitrarily. Then you take the averages of these things. Okay? So that there is a sort of two-step conditional expectation process. So first, you remove all the off-diagonal things and just keep the diagonal things. Then you take the average of the diagonal. So that is how the conditional expectation works. Okay. So that is I will again skip that. Okay. So what does then? What can we say then? So then. So I got two conditions for the existence of this unitary orthonormal basis. One is that the inclusion should be such that you have these dimension vectors to be Fermat-Frobenius eigenvectors. And the second condition is that the conditional expectation E itself is sort of uniquely determined from this. Okay. Now we ask whether we can actually construct a basis in this kind of situation. Okay. And we are able to do it for some special examples. So the work of Crane et al., that one show the example when C is contained in this kind of thing. How to do it, they tell. Okay. Just a very special case when the smaller algebra is just the complex numbers, and that is done by them, where you have usual Hilbert spaces. Okay, so the general thing, how do you do it? So we need this thing called the succulent matrix, and which starts with the Fourier matrix. The Fourier matrix you have already seen here is the exponential ijk by n. So I am just using the epsilon notation to say that it's exponential. Okay. So then you pre and post multiply by diagonal matrices. Okay. So what happens when you do that? You get matrices. Okay. So this Fourier matrix. Okay. So you have the diagonal things, and you pre and post multiply by the Fourier, and it's inverse. So what you get then are called the succulent matrices, and they will be matrices like this: some A0, A1, etc. Then A1, A0. You mixed it up, I think. It sort of rotates. The rows, right? That is called the succulent matrices. So you need two types of matrices. One is this from the diagonal matrices, you do the Fourier transform, and you get this. Okay. So I need to multiply by the diagonal matrix from both sides of the succulent matrices. Okay. So then what we get is called the quasi-succulent matrix. So so inside I have succulent matrices. Okay, I should have written it here. So I think I can skip that. So we are able to write down the unitary orthonormal basis, some special cases. One special case when the smaller algebra is abelian, B is CR, then we are able to write down a basis. Okay, and the basis is pretty complicated, but we are able to write it in that case. And another case, okay, I will not go into the detail. It is based on the succulent matrices and some exponentials of this. And another case we are able to, so what we note here, the basis would look like this. You have two specific unitaries and the powers of that. Okay. So earlier, if you remember the wave basis, it was all powers of V and all powers of U. Whereas here I have specific the same power both. So that gives a unitary orthonormal basis when CR is contained in E, subject to those conditions. Okay. So I will not go through. generally, when the first one is abelian, we are able to do. Okay? I will speak further. Okay. So this is the case. CR inside the generalizing that way unitaries, we are able to do it. But here, in the case of A, you see it is the same MN. Not MN, 0, etc. The same MN. Copies of MN. Okay? So, let me, okay. So then there are, see what is the goal? The goal is to get unitary orthonormal basis whenever this B inside A and those necessary conditions are satisfied. I said there are some necessary conditions. It is. So in that effort, this Crane's example, their construction gives you C inside something. So we do it for other cases, and we see how we can construct new things from the mode. So if you have one construction thing, we can compose, we can take tensor product, we can take direct sum. So various ways you can try to construct the new ones from the mode. Okay, so that is the thing. Okay, and there is something called Jones basic construction, which says like if you have for B inside A, you have a unitary basis, then there is something which you can construct by sort of reflecting the inclusion matrix, taking the transpose of the inclusion matrix. So there also one can construct. So this way we can construct more and more unitary orthonormal basis. So we are able to do it for a big class. Big class, whenever the bigger algebra is the full matrix algebra or like that, or it is fully abelian. Such special cases we are able to do. The general case is still open. We don't know whether one can construct, whenever these conditions, necessary conditions what we have shown, whether they are sufficient or not, we don't know. Okay, maybe I stop there.
Thank you very much. So, are there any questions? Yeah.
And you yourself mentioned there is some similarity with the representation
Yeah.
of finite groups.
Yeah.
Schur-Frobenius theory.
Yeah.
So have you found that kind of
We get examples from there. One can get examples from the group
what
representations.
would be the candidate for the conditional expectation? That's what the main case.
The conditional expectation will be similar.
No, in the what I'm saying is that can you map the Schur-Frobenius theory of irreducible representations of finite groups?
Yeah. So see that all those things will actually basically correspond to C inside something.
See,
The bigger algebra, direct sum of n minus. Yeah.
and then tensor product of two irreducible representation is breaking it.
Yeah.
That also can be.
Yeah, that can be done. That can be done. So you can do. Yeah. So the final summary is that we are able to construct the things for some special cases, but whether these conditions are sufficient, means whether we can always construct unitary orthonormal basis in these cases, we don't know.
Thank you. So, any further question you can ask for at the coffee time. So, let us thank the speaker again.
Thank you, sir. I would like to invite the chair to give the token of appreciation to our speaker right now.
Yeah, maybe, yeah, they don't want the light. Yeah, they don't. It's like okay, this. Okay, thank you.
Now we will go for a small tea break, and I expect everyone to be back by 10:55.
That is even harder, I think. Trying to classify all these unitary orthonormal. Yeah.
non-competitive LP setting, so which is actually also a very natural object to study. It is not a mere generalization, because many people already said that von Neumann algebra is kind of the model of statistical mechanics, or furthermore, maybe in physics rather you try to find answer for this following question. So for non-competitive L1 space or von Neumann algebra, you take positive construction whether this kind of object converges in certain norms or more general sense. Okay, so the study of nebulae decomposition. Okay, so earlier with my student we solved nebulae decompositions for even it was known in classically also. I think the Bartholomew Roy he proved for Z actions, but we proved for arbitrary amenable semigroups. Okay, I think he wrote a lot of old paper where he proved that for Z actions. So, but we also prove for any amenable group or any amenable semigroup for any von Neumann algebra. So recently we come with this, but we brief what is the von Neumann algebra is. So you have H is a Hilbert space and M is a von Neumann algebra if it is W closed or it is W complementarity itself. So then a finite von Neumann algebra means there is a faithful normal trivial state. Okay, so and then of course the p-dual of M von Neumann algebra always have a p-dual, and the p-dual sits inside the dual. Maybe TSSRK was saying similar to those things. So maybe the notations are different, but okay. And rho belongs to M is positive linear functional, and the pair will be maybe you can call non-competitive measure spaces, because M is actually a generalizer of the infinity spaces. Okay, so and then a G is a semigroup with right infinite Haar measure. So G is amenable if there is a sequence of compact set such that this kind of thing holds. Okay, so basically it is like a approximation, some kind of approximation property that your group has. Okay, so okay, then for the non-competitive setting, so we'll replace L infinity by von Neumann algebra and LP classical LP space by some sense of non-competitive or quantum LP spaces. Okay, and then actions, G is the action on M rho. So basically alpha G M to M is a positive linear map such that they satisfy this, and sometimes we refer this system as a covariant system. Okay, and again, and for given a amenable group, and you consider this average, and you can talk about its convergence in various for X belongs to M or more general space, bigger space LPM. There are a lot of studies, so maybe I will not go to all these details, or maybe in the brief in some history. So I will go to my work, our work maybe directly. So what is the meaning of the big question is what is the meaning of pointwise convergence here? Pointwise convergence here in the non-competitive setting. So before coming to that, let me just quickly state the nebulae decomposition that we want. Alright, P0 is the set of projections, non-zero projections, and you consider this average. And X again, now in the non-competitive it's called weakly wandering. If this kind of average converges in norm, not weakly or very sharp convergence. Okay, and then this for some point of time in studying this theorem, for some people are already listened this talk, I guess, but not the same statement. So, but other people may look at same statement, although it is not statement. So it is earlier we always used to have assume maybe the finite von Neumann algebra, but we improve it. Semi-finite von Neumann algebra with faithful normal trace. This need not be a trace, but it is a semi-finite trace. So that means the tau of one need not be one. It could be infinity. Okay. And MG is a covariant system. Then so for there exists a state rho in M star such that S rho is U1. That means given a equivalent system, to perform anything meaningful calculation, you need to have a invariant state. Okay. So but what you can do that. So in a corner we always get an invariant state, and another corner will have a get this weakly ordering vector. The support is E2 and another support is E1, and the sum is 1. Okay. And indeed, actually, we proved this not only in semi-finite quantum algebra, we proved more the general setting amenable group action, but with a kind of Markov amenable actions, which like commutes with the very symmetric thing. That means commute with the modular proportional group. Okay, in that case, we use some cross product trick and calculated this also. Okay, and then I how much time I should have? Maybe I have 5-6 minutes, I guess. So you given a m and tau, you consider the L2m tau, and which is a GS Hilbert space, and then you can again, I mean, you can in non-commutative setup you can define LP, but you have to go through certain non-commutative integration and one more affiliated unbounded operators and the spectral theorem. So I do not have much time, but maybe I'll skip little bit here. Okay, what we can say that. So yeah, the last theorem. So you can certain like you can think of the trace class operator here, but it is you are in any fundamental algebra. So all those x, which is like a measurable function and whose integration is finite, or then you call that to be L1. And again, you can this concrete representation. You can actually see that this is the pre-dual of the fundamental algebra by via these maps. Okay. Okay. So now, but this maybe I will take 2 minutes because this is one of the main theorem. What is the analog of pointwise convergence in non-commutative setting? So pointwise. So maybe be careful a little bit here. So let Fn be a sequence of function. It converges pointwise. Then by Elthuruth theorem it says that on a big set it actually converges uniformly, right? Okay, now this is the picking point to generalize this definition to the non-commutative setting. That means given epsilon there exists a set whose complement measure is small, and you can replace the mu by kind of tau of this, then this converges in uniformly. So similarly, given a sequence in fundamental algebra or LP spaces, so given epsilon there exists a projection is such that whose complement whose measure of the complement measure is small, and it converges in norm up to multiplication projection either from one side from the other side, because you are in non-commutative setting you have to consider both conditions. But classically you have one side is enough because they are commutative setting. Okay. So now this theorem is quite active for even 19 with the first theorem of Lens, and there are series of papers. So maybe we have also a couple of papers there with my speech student here. So we did for various group actions, but not for construction report. Okay. So if T be a bounded normal map and T star is a map is given by this. So we go and for pre-dual map, dual map. Sometimes we use the same notation, but I hope it is not much confusion. So okay. So if we write for P belong from the pre-dual, and if we write T5, that means it's a pre-dual map and it's acting like this way. Okay. Okay. So now T is a positive construction, it is continuous. Then you consider this average where mu is belongs to the pre-dual. Then this kind of theorem is called maximal inequality. To prove anything, any economic theorem, you have to prove certain kind of maximal inequality. If T from M to M a positive construction and T1 less than 1 and T is a state invariant, then for all N there exists a projection such that you can control the projection and measure a mod of A mu x is less than epsilon rho x for all x belongs to this corner and for all n 1 to n. Okay. So then using this theorem you can easily prove your algebraic theorem. Okay. So Again, this is the definition I already said, but for M, but same definition in the non-commutative we extend for LP spaces or L1 spaces also. So bilateral, this is called bilateral almost uniform convergence. Okay, and then if you have a T is a from L1 to L1 positive construction, and then pre-dual map you can define it this way. So it is, yeah, 3 minutes maybe. I take 3-4 minutes. I think 3 minutes, 2 minutes maybe. So okay. M be a fundamental algebra and T be a positive construction, and then this is the same theorem. Yeah, I think this same theorem somehow it got thing again. Okay. Yeah. Now if you have a T is a M is a fundamental algebra. Sorry. In this case we assume M is finite fundamental algebra and T is a positive construction. Then the sets where phi and phi converges in BAU is closed in this thing. And then we somehow produce a dense set which is like this. If you consider W to be this, then W minus W is a dense in M, and then we can conclude the. So if you have a MT is a kernel and this be a spatial state, then this average converges in bilateral almost uniformly. Okay. And convergence in measure, you rather one projection, you multiply sequence of projection from both sides. Okay. And then this is my maybe second last theorem. If T be a positive construction and you consider the E1 and E2 B2 projection as in every decomposition, then first corner for all B belongs to L1 to L1, there exists a B hat such that the A and B converges in BAU, and in particular A and B converges in measure because this is a stronger. Okay, and then for all B in L1, this converges in measure in 0. Okay, and then if you assume one more condition that if T is a positive construction and T is a Lampert T, that means it takes orthogonal projection to orthogonal projections, then this average actually any T you do not need to assume it is as it preserves some state, is that, nothing. Any positive construction, then the ergodic average converges in measure. But one corner will have a stronger convergence, pointwise convergence, but if you have Lamperti contraction, so this converges in measure. So for, I think I am done. Yeah, so there is some reference, but I want to say a couple of words. So this T is a positive, we have assumption that T is a Lamperti contraction, but I think for general T, it is open. In fact, not only in L1. So if you just take this following simple problem, T is from non-commutative LP space to non-commutative LP space, positive construction P between 1 to infinity. Then I think there is any it's an open question. But I think the Lamperti contraction is solved. But general positive construction it is open. But for the commutative setting, the Akakulu's original technique is also he assumed that first solve these kind of questions for Lamperti contraction in classical case also. But in the classicals, convex combination of Lamperti contraction is dense in all the positive contraction. But in the non-commutative major difference is convex combination of positive contraction need not be dense in non-commutative space. So classical tricks or technique will not work in this context. In fact, we submitted some of the papers and authors said maybe it will be, you need some extraordinary techniques to solve this question for non-commutative for full journey. I finish. Thank you.
Thank you, sir. I would like to invite the chair to give a token of appreciation to our speaker.
Thank you.
Let's move on to the next session. Our next speaker is Professor J. Narayanan here. I would like to invite the chair, Professor Rao, to introduce him.
Oh, sorry.
So welcome to this talk by Dr. Narayanan. Actually, he is a PhD from ISI and he did his postdoctoral work at IIT Kanpur and he is currently the chairperson of the math department at IIT Palkad. And today he is going to talk about strong wall proximity of the space of compact operators on universes.
Thank you, TSS. So, first I would like to thank the organizers, especially Professor Narayan, for this invitation. Yeah, so this talk is basically coming from a Banach space theory. So, this is purely a traditional approximation theoretic probability in a Banach space setting. And I would like to consider the same problem in the space of operators. Okay. So, in the first part, I would like to give a survey of the theory happening in the abstract Banach spaces, and in the second part I will consider the space of operators. Okay? So the problem, the problem I was talking about is if you consider your the traditional continuous function space and you can consider the polynomial, space of polynomials of fixed degree. Okay. Now you can talk about for any given continuous function f, can you get a polynomial which approximates that continuous function? But here the difference is that the degree of the polynomial is fixed. So what do I mean by approximations? If you take the distance from f to this polynomial space, whether this condition is satisfied, whether the distance is at the polynomial in Pn. Okay, and it's already people have studied this problem, and it is known that for every continuous function f in CAB, you can always find a unique best approximation, okay, from Pn. Okay, so motivated by this, people generalize the problem in an abstract Banach space theory, Banach space setup. So you start with a subspace X, and if you consider any point from the Banach space, can you get a best approximation from that subset? Okay. So now the setup is you start with a subset of X, of course non-empty, and if you start with an arbitrary element in the Banach space, does this distance is attained at some point in the subset. Okay. So of course there is no reason to believe that such a point exists, and if at all it exists, we don't know how many points will be there in that set of best approximation. Okay. And another problem people considered is, so if you take an X in X, then you can always consider set of all elements in the subset K for which this best approximation is attained. So the best approximation exists. Okay. So this in many cases this is a set valued map. It will be a single valued map, and in many cases this might be empty. Okay. So the question is, when you vary this point X, what is the change happening in the set of best approximation? This is the regularity property. You are basically looking at the regularity properties of this map, and this map has a name. This is called the metric projection. And when you consider Hilbert space and the subspace to closed subspace of the Hilbert space, then this metric projection coincides with your traditional orthogonal projection. Okay? So what I am going to consider in this problem is kind of a variant of the second problem. So when you change the point x, how the set of best approximants vary. Okay? And we would like to precisely see whether you can impose any condition on the subset or on the subspace K for which you can expect some regularity property for the metric projection. Okay? Right, okay. So now I'll make the thing precise. So if you start with a subspace M of a Banach space X, and if you start with an arbitrary point in X, so the PMX denotes the set of all points in M, that is from the subset, for which the distance is attained. You know that the distance of X with M is precisely the infimum, and you are basically asking whether that infimum is attained at a point. Okay? And if it is attained, then we call that subspace to be proximal. If it attains for every point X, then we call that subset to be proximal. And since it's a problem of attainment of the infimum, the obvious thing which you can impose on the subset is the compactness. But you know that in an infinite dimensional Banach spaces, you will not have adequate compact sets, which makes this problem slightly non-trivial. Okay? So wherever you have nice compactness assumption, then you can expect a positive result. Otherwise, it's something non-trivial. So for instance, you know that in a reflexive space, or if the subspace is reflexive, then the closed unit ball is compact with respect to the weak topology, and there you can expect the attainment of that infimum. So if you start with a reflexive subspace of the Banach space X, then they are going to be proximal subspace. So the map I was referring was, if you start with any point X, and that point is mapped to the set of best approximations. Okay? And that map is called the metric projection. Okay? So precisely what I am going to consider is, do you have any condition on the subspace M for which this metric projection is continuous, maybe upper semi-continuous, lower semi-continuous, or even continuous. Okay? So I want to impose some condition on M so that I will get some regularity property for P. Okay. So the space subspace which I am going to consider, or the subset which I am going to consider is called the strongly proximal subspace. So you start with any proximal subset of Banach space X, then it is said to be strongly proximal. So if you look at the so if you look at this set, so Pkx is the set of best approximation, and Pkx delta need not be a best approximation. Element need not be a best approximation, but you can see it varies from the norm of x minus y, and distance varies only by delta. So you can see it as a set of nearly best approximates, and the question is whether this set comes closer with respect to some metric, which I will come later, which metric we are going to consider. Okay? And one can easily observe that this is equivalent to saying if you start with any sequence, so you have this distance, and you can always see that there exists a sequence from Yn which converges to this distance. You can just apply the definition of distance and see that you can always find a sequence from the subset K such that the norm of x minus Yn converges to the distance. Okay, and such sequences have a name. It's called a minimizing sequence, and the strong proximality is equivalent to saying, demanding that minimizing sequence and Pkx comes closer. Okay, so we are expecting that distance between Yn and the set of best approximation comes closer to 0. So the thing is that Pkx and Pkx delta should be close enough. for K to be strongly proximal. Okay, since there are some convergence assumptions and so you have a sequence and here you are expecting some kind of a subsequence, convergence of some subsequence. So if you have the subspace to be a finite dimensional subspace, then you can expect this. Beyond that, it's always hard to see whether it's strongly proximal or not. Okay. Yeah, so one of the immediate observations, once you assume the subspace to be strongly proximal is, or subset to be strongly proximal is, you can have a upper semi-continuity of the metric projection. The upper semi-continuity means it's the same way you define upper semi-continuity of a single-valued map. So for every epsilon positive, we are expecting a delta such that if you consider the neighborhood of pkx, then that should contain pkz if z and x are coming closer. Okay? So when x and z are coming closer, pkx and pkz should be close enough. And you call the set valued map metric projection pk is said to be host of metric continuous if it is continuous with respect to the host of metric. It is defined like this. Okay. So one can easily show that if it is strongly proximal, then the corresponding metric projection is upper host of semi-continuous. Okay. But the converse need not be true. The reason is if you consider any codimension 1 subspace. By codimension I mean Y is said to be of codimension 1 if the quotient space has dimension 1. Okay. So if you they are precisely the hyperplanes in Banach space. So if you consider hyperplanes, then on metric projection onto the hyperplane is always host of metric continuous, but all hyperplanes are not strongly proximal. Okay. So if the hyperplane has to be strongly proximal, then the underlying function which defines the hyperplane should satisfy some differentiability condition. Okay. In general, you cannot expect the full continuity, the host of metric continuity when the underlying space is strongly proximal. We have only the semi-continuity, but when you consider the C of k space, the space of continuous functions on C of k, and if you start with a finite codimensional subspace, then you can expect the metric projection to be continuous. Okay. Here, finite codimension, as I said, I mean the quotient space has to be finite dimensional. Okay. Now, it is well known that the dual of C of k spaces is isometric to a L1 space for some positive measure mu. Okay? So it is since the problem, the continuity problem is solved in C of k space, it is easy. One can easily ask whether this problem works in the L1 p-dual space. So what is an L1 p-dual space? So L1 p-dual space is a whose dual is isometric to capital L1 space for some positive measure mu. Okay. So if you take any compact host of space K, then dual of C of K is isometric to L1 mu for some positive measure mu. Okay. This is a well-known result in Banach space theory. And of course you know that C0 is an L1 p-dual space because its dual is L1. Okay, so C0 and C of k are the popular L1 p-dual spaces, and once you have a result in Banach space theory, if you have for any Banach space theoretic problem, if you have a result in C of k, you can always try to generalize it to L1 p-dual spaces because that's a huge big class of space for which many results hold. Okay. So you can conclude that if Y is a finite codimensional, strongly proximal subspace of an L1 p-dual space, then Py is host of metric continuous on X. Okay. So one technique in Banach space theory where you can shift from a space to its bidual. Maybe the bidual is already defined in the first class, first lecture. So if you have a space, subspace in a Banach space X, then you can look at its annihilator. Annihilator is sitting inside its bidual, its dual. Okay, and you can further do this. So you have bi-annihilator. That means the annihilator of Viper in the second dual of X. Okay, so many times you can try to draw some relation between Y and Y double top in double star. Okay. So the first step to prove this result was to establish a relation between strong proximality of Y and strong proximality of Y double top. Okay. So we can prove this. We could prove this for finite codimensional subspace Y. So the result is if Y is strongly proximal in X, that is equivalent to saying Y double top is strongly proximal in X double star. Now the advantage of having this result is, if you know that X is an L1 pre-dual space, that is, if its dual is capital L1, then a famous result of Lindenstrauss tells you that X double star is isometric to a C of K space for some compact Hausdorff space K. Okay? So what we did in this proof is, if you assume here strong proximality, then you can move to Y double per in X double star, but X double star is not to be a CK space. You solve the problem there and then argue using the same, you argue back saying that Y is Py is Hausdorff metric continuous. So if you club the Lindenstrauss result with this result, then you can easily move from the subspace to its move from the space to its bidual. Okay. Now, so once done, or when you have developed the theory for the subspace, in the sense that you are expecting the best approximation to come from the subspace, then you can ask whether you can take the best approximation from the closed unit ball of that subspace. Okay? Or you are expecting a bounded approximation. Okay? So that is called ball proximal. So if you are expecting the best approximation from the closed unit ball of the subspace, then you call that condition to be ball proximal. That is, if Y is said to be ball proximal, if the closed unit ball is proximal in X. Closed unit ball of Y is proximal in X. Okay? And analogously, if the closed unit ball is strongly proximal, then you call the subspace to be strongly ball proximal. Okay? So it can be proved that the proximal subspace need not be strongly, proximal subspace need not be ball proximal. But the other way around can be easily observed that ball proximality should imply strong proximality, and strong ball proximality will imply strong proximality. Okay, so the converse of this doesn't hold, because there is an example by Professor St. which gives you a renoming of Cicero where there is a subspace which is proximal but not ball proximal. Now, so we can see whether there is any class of subspaces for which all these properties holds. Okay, do you have any class of subspaces in an arbitrary Banach space for which this ball proximality holds? Okay, so for that we define something called L projections and M projections. So this basically. So you have a Banach space X, then you can consider the projection on X, okay, and this projection is said to be an L projection if it's a projection and it also satisfies this condition. That means the norm splits through the kernel and its range. Okay, and it's said to be an M projection. Instead of this splitting, it comes as the maximum of norm of Px and norm of x minus Px. Okay, so and a subspace is said to be an L summand if it is the range of an L projection, and it is said to be an M summand if it is the range of an M projection. Okay, or in you can see that if you have a subspace J in X, you can see whether X is the direct sum of J with some happens to be with some other with other subspace. Okay, and here it is said to be an L summand if this direct sum happens, that is for every X you will have a Y Z such that norm of X will be norm of Y plus norm of Z. Okay, then we call J to be an L summand in X. Okay, and we call a subspace to be an M ideal if that is the annihilator of J. So J pub is a subspace of the dual space X star. So what you demand is X star is J pub direct sum subspace. Okay, and this is the L1 direct sum. Okay, so there are some nice properties for M ideals in Banach spaces. That is, the Han-Banach extension is going to be unique an M ideal in Banach space. Okay, so standard examples are, so C0 in L infinity is an M ideal, and in C of K spaces it's completely characterized that it is set of F in Ck such that the function vanish on a fixed closed set. Okay, and the space of operators, so Kx is an M ideal in Bx if you consider X to be little lp or C0, but when you take P equal to 1 or infinity, it's not going to be an M ideal. Okay, right. So how does this connect with the proximality, or what is the proximality property of M ideal? So one can prove that M ideals are strongly proximal, and the corresponding metric projection is cost of metric continuous. Okay, and then but going forward, the M ideals need not be called proximal. That is, the unit ball of closed unit ball of M ideal need not be proximal. So because if you consider kernel of this function 1 in the disk algebra, then that's going to be an M ideal, but it's not going to be ball proximal. Now, when will M ideals become strongly ball proximal? So if you consider M ideals in L1 Friedel spaces, so if you consider M ideals in a Banach space whose dual is isometric to L1, then that's going to be ball proximal, and you can see that the metric projection onto the closed unit ball of the M ideal is going to be cost of metric continuous. Okay, and in L1 Friedel space, you can further see that there is no direct distinction between this convexity problem and the subspace problem. So strong proximality is a subspace problem, linearity problem, but strong ball proximality is a convexity problem. So strong proximality, you are looking at whether the subspace is proximal, and in the strong ball proximality case, you are looking at whether the closed unit ball By is or the convex set By is strongly ball proximal. Okay, in L1 Friedel space, if you consider finite coordinate subspaces, then these two concepts coincide. Okay. Now, coming to the problem of space of compact operators, so whatever we have done in C of K, so we would like to look at whether those things holds in the space of operators. So first of all, you can using some operator theoretic techniques, you can prove that KH is ball proximal in DH. And here it doesn't say, not only says that the best approximation exists. So for example, if you start with a self-adjoint operator, you can get the best approximation from compact operator, which is also a self-adjoint operator. The same thing can be done for positive operators. You can prove that. So whatever best approximation you produce, the same, if you start with a self-adjoint operator, you are going to get a self-adjoint best approximation. If you start with a positive operator, you can get a positive best approximation. It's separable. Good, it's separable. Okay. So the question is whether, so prove the ball proximality of K of H in D of X, you can ask whether strong ball proximality holds for compact operators. Okay. So for that, we first look at, to address this, we first look at the following problem, that is whether an M summand is strongly ball proximal. We already know that M ideals are not ball proximal, and every M summand is going to be an M ideal. Okay, because so there is always this relation which works quite nice. There is a duality relation. If X has this decomposition, then X star will decompose through its output. Yeah, so some other thing. Okay. Okay, and it goes back. So if J is an M summand in X, F is an L summand, and if J is an L summand, then J is an M summand. So there is this duality relation holds. So you just need to take the adjoint of that projection. So if P is an L projection, then the adjoint of P is an M projection, and vice versa. Okay. So M summands are M ideal, but you know that M ideal need not be ball proximal. So under a strong assumption, you are asking whether it satisfies something more. Okay? So it's not true in general. You can renome the space C0. So C0 not with the usual norm. You consider y norm of y to be norm of y infinity plus that sum, infinite sum. Okay, then you can prove this is a strictly convex space. So in the original norm it's not strictly convex, but you can renome it to be a strictly convex space. And with respect to this renoming, this By is not going to be strongly proximal in the same space. Okay, so you are not going to the next space, any bigger space. The closed unit ball is not going to be strongly proximal in Y itself. Okay. Now what you do is that you just take a direct sum of Y with an arbitrary Banach space, and you on X you endow this direct sum norm. Okay, that is the norm given by infinity norm. So precisely the norm there would be you take norm of X to be maximum of norm of Y and norm of Z. If you have the decomposition X equal to Y plus Z, you consider this particular norm. So Y is sitting inside X as an M summand, but it's not even strongly proximal in a subspace Y, so you cannot expect it to be strongly proximal in a bigger form. Okay, so M summands need not be strongly ball proximal. So actually here you can observe that the only problem here, this is not a coincidence. In general, if this problem is not there for an M summand, then you can get strong ball proximality for that M summand. So that is the next result. So for an M summand to be strongly ball proximal, you want the space, you want the closed unit ball of Y to be strongly proximal in Y. Okay. So whatever issues we have seen here, if that doesn't happen, then you are in a nice figure. You will get an affirmative answer for this question. Huh? 5 minutes. Okay. we always try to look at what happens to the same property in the bidual. Okay, so you can prove here that, so in general in Banach space theory, if you have some property on the bidual, then you expect it to inherit to the underlying space. Okay, so one can prove that. We can prove that if y double perp is strongly proximal at all points of x. Okay, note that here you don't require the assumption to happen for the y double perp is a subspace of x double star. Even then, I am not assuming the condition to be satisfied on full space x double star. So under the canonical embedding, x is sitting inside x double star, and my assumption is only for those points inside x, not on x double star. So even if the condition holds for points in x, still I can conclude that y is strongly ball proximal at x. Okay. Now using this, we can derive something. So let me just write it down. So the space of compact operators on H inside B of H, this is an M ideal. Okay, that's a result of Dictionary. Okay, and if you consider this is an M ideal, then it means that K of H perp inside B of H star, the adjoint of B of H, is an L summate. Okay, if you further go ahead, you can see that K of H double perp is going to be an M summate in B of H double star. So by the previous theorem, it is enough to prove K of H is an M ideal in B of K of H is strongly ball proximal in B of H. It is enough to prove that K of H double perp strongly ball proximal in B of H double star. So if you establish strong ball proximality here, it will directly translate to K of H in B of H. Okay, but if you recall the previous result of M summand, so M summand is strongly ball proximal if that closed unit ball of the subspace is strongly proximal in Y. Okay, so you can prove this problem if you settle this problem here, and to settle the problem here, you just need to prove that K of H double perp, that is the closed unit ball of K of H double perp is strongly proximal in K of H double perp itself. Okay, but K of H double perp, you can see that for any subspace it is isometric to K of H double star, and now you are asking whether the closed unit ball of K of H double star is strongly proximal in K of H double star itself, right? But K of H double star is B of H. Okay, so you can solve this problem if you could prove that the closed unit ball of B of H is strongly proximal in B of H. So we couldn't prove it for the entire case, but we could prove it for a dense subset of B of H. So for example, if you consider operators which are strongly subdifferentiable. So strong subdifferentiability means if you consider a Banach space and it's known, we say a point is strongly subdifferentiable if this one-sided limit exists uniformly. Okay, so in B of H, the strongly subdifferentiable operators are precisely those operators which has one as an isolated point in the spectrum of its modulus. Okay, so what we proved is we could prove that the closed unit ball of B of H is strongly proximal and operators which are strongly subdifferentiable. And it is known that the set of all operators which are strongly subdifferentiable forms a dense subset of B of H. Okay, and I'll not say much about this. As a corollary, we can prove that closed unit ball of B of H is strongly closed unit ball of K of H is strongly proximal in K of H because compact operators are also strongly subdifferentiable. Okay? Yeah, so one can try to extend this problem under the, if you consider any Banach space X for which Kx is an M ideal in B of X, you can try to extend this problem in that setup. Okay, Elthuruth.
Now I invite the chair to give a token of appreciation to our speaker. Let's move on to the next session. This is the last talk of the morning session. So the next speaker is Professor Kiran Kumar, and the chair for this session is Professor Panju Gopal Vikram. So I invite the chair to introduce our next speaker.
Finally.
So it's my pleasure to introduce B.B. Kiran Kumar. So from University. We will be talking on synthetic spectrum of nucleation operators.
Thank you. So let me thank the organizers for this invitation. So I'm going to talk about synthetic spectrum of interdimensional operators. So let me just mention that in quantum information theory, the finite mode Gaussian states arise quite naturally, and there is an associated with there is a covariance matrix, and something called Williamson normal form is applicable, and I will explain all these things in detail. Don't worry, I will just explain this diagram. So, and therefore synthetic eigenvalues comes there, and when the quantum, the continuous variable quantum information theory comes into picture, infinite degrees of freedom comes for the quantum Gaussian state. So then, instead of this matrix, covariance matrix, there will be an operator coming into picture, which we call the Gaussian covariance. Okay. So there we need a kind of infinite dimensional analog of all these things. So now I will explain this one by one. So the basic thing which you need to keep in your mind is that our underlying field will be always set up for real numbers instead of complex numbers, which is the usual thing. And another thing is that we will be considering even dimensional or even order matrices. Okay? Okay. So this is the Williamson normal form, which was published in 1936 due to John Williamson. So to explain this, recall that we have the finite dimensional spectral theorem for operators, or in the real case, over the real field, you have spectral theorem for symmetric matrices. Okay, so it's a kind of diagonalization thing. So this is similar to that, but what happens is that we are in a symplectic space here. So as I mentioned, we consider matrix of even order, positive definite matrix of even order. Then there is a symplectic matrix. I will explain what is that. So unlike the orthogonal matrix which we had in the spectral theorem, we have a symplectic matrix here, such that this will happen. So here D will be a diagonal matrix of order n. So two copies of D will come here. So that this is again a kind of diagonalization. So this works for every positive invertible matrix T. Okay. So we have a positive invertible of matrix of even order with real entries. So there, the symplectic normal form due to the Williamson normal form due to John Williamson will work. Okay. Now here so I have to explain a couple of things. So one thing is that what is a symplectic matrix? So symplectic matrix will replace the role of orthogonal matrix here. So this is a symplectic matrix. What you do is that you consider this J minus I, and symplectic, so we call L is symplectic if this identity is satisfied. That is L transpose J L equal to J. So in the orthogonal matrix, instead of J you consider identity matrix, and then you will get the usual orthogonal things. In terms of compass, no, but compass is different actually. So there you will consider I too. Parameters of I. Now this J, actually J will give you a symplectic form. That's the thing. So this is a special kind of thing. And this you see J satisfies the property that it will be skew. So to make it, so it's automatic that you need even dimension. So otherwise skew Hermitian matrix will have in the odd dimensional case there will be a 0 coming in the spectrum and create. Yeah. So now one more thing. So this D is unique up to the order of entries, and elements of this D, the diagonal entries of this D are called the symplectic eigenvalues of T. So this is how it is being defined. So after 1936, this particular was very much applicable in quantum physics and several other areas, and symplectic geometry also. But one thing I noticed is that till 1999 there was not much mathematical articles appeared, which referred to this article. So after 99, now if you see the math Senate, more than 200 papers have cited this particular article. So maybe that is connected to the area of quantum information theory and so. I will explain some of them. So now, yeah, this is something I mentioned. So in the finite world quantum quotient theory, this Williamson form gives you a canonical representation for this quotient covariant matrix. And now the question is, what happens in the infinite dimension? So again, H is a real Hilbert space, and so you have the same thing. If T is a strictly positive inverted operator on H there is some H, then you have a symplectic transformation there. But now, what is the symplectic transformation? I will introduce. Okay, so we cannot rely on the thing, the financial thing. So you have a symplectic transformation. Such that you have the same thing, but now the D is now not a diagonal matrix. Instead, there is a positive operator appears there. So D is a positive operator on H. So another thing is that this D is again unique up to conjugation by orthogonal transformation, so that you can define the symplectic spectrum of T to be the spectrum of D. Okay. So here what I missed is this definition of symplectic transformation in the infinite case. So what you do is that H is a real Hilbert space, and you consider the identity on H, and you form this block operator. So Q again the same thing. So Q is symplectic means this identity is satisfied. Q transpose JQ is J, but remember Q transpose is now the transpose operator as an operator from S. So this is from S direction S to K, there is some K. So the transpose will be from the dual space and so on. But you can identify as block. So now, so these people, so yeah, this is the result. I mean, so this is the international Williamson form proved by these people in 2018-19. Okay, so after that they gave lectures in conferences like this, and I also attended. I got interested in this, and fortunately that time Mary joined with me, so I suggested her to work this area. So we started working on this because we can define symplectic spectrum here. So I was this is here. I mean, you consider this J here to be identity is on H, this J, and you need this identity. So transpose will be matrix transpose. I mean, transpose is. This here transpose means actually from the dual space to this thing, but this is a 2 by 2 copy, so you can type. This is over real. It is a real Hilbert, so that's the only difference. Yeah, this is the same, but this is a real. That's why the transpose. Okay, so so. Till then I was working on spectrum and approximation kind of things, and so then I thought, can we do this for symplectic spectrum? So definition of symplectic spectrum is here now. So every positive operator you can have a thing like this, positive operator on the real operators like this. So we started looking at this problem. So then we observed that there is a group of people working on the problems of finite dimension things. So what they do is that whatever things are available for eigenvalues like inequalities, Riskies inequalities and several inequalities, they try to prove it for symplectic eigenvalues, like in theorems and so on. So what we did is that our results are of two types. One is that whatever things they do in the finite dimension thing, we try to extend infinite dimension things whenever it is possible. And another thing is, can we approximate? So these are kind of approximation kind of results. I mean, you consider an infinite dimension operator and look at the symplectic spectrum. So try to approximate it using the finite dimension truncations. I will explain these two problems. Okay? Yeah. Yeah, one very important thing I wish to mention. So as I mentioned at the beginning, there's a quotient covariance operator coming into picture instead of the covariance matrix, and which contains most of the information corresponding quantum system. So our results are applicable for this class of operators. This is very important. So I will explain it in detail. Yeah. So here is a final dimensional result due to Rajendra Bhatia and Tanvi Jain. Came in 2015. What does it tell you? So you have a 2 by 2 positive definite matrix. You list down the eigenvalues in the increasing order. So this is a positive definite matrix. So what you can do is that, so since it is a positive definite matrix, you can arrange eigenvalues in this way, lambda 1, lambda 2, etc., lambda n. So this increasing order I denote by this arrow. So this arrow shows that I arranged it in the increasing order. Okay? If you find a downward arrow, that means I arranged it in the decreasing order. Okay? So that's the important thing. So what they proved is that, so you start from a even order positive definite matrix. So it has 2n eigenvalues and n symplectic eigenvalues. So symplectic eigenvalues will be n, and there will be 2 copies of d are there, so n will be, only n will be. Yeah, that is, I think you missed the very first slide. Yeah, so, yeah, this is the Williamson form. So for every t, there's a diagonalization like this. So eigenvalues of this d are called the symplectic eigenvalues. And in the infinite dimensional case, you have the same thing. Yeah, so spectrum of d is called the symplectic spectrum of t. So, yeah, this is due to these people. So what they proved, you arrange them in the increasing order, both of them, symplectic eigenvalues as well as. No, this is final dimension. This is for matrix only. I am telling the final dimension matrix result first. Okay. So you arrange them in the increasing order, and then you have the interlacing theorem. I mean the one eigenvalue, so between the jth eigenvalue and n plus jth eigenvalue, the jth symplectic eigenvalue will lie. So this is the interlacing theorem proved by them. Okay. So now, as I mentioned, shall we have the similar thing in the infinite-dimensional context? So the infinite-dimensional context, the challenges are plenty. The first thing is that this identity, this inequality itself contains the dimension n. So you need to make it free of dimension first. Okay? So that's the first thing. Second thing, as you know, infinite-dimensional operators need not have eigenvalues or symplectic eigenvalues. So a natural choice would be compact operators, compact positive operator, compact positive or self-adjoint. But the point is that the Williamson normal form on the infinite setting is applicable for strictly positive operators. Compact operators on infinite will not be invertible. I mean, so 0 will come into the picture. So you cannot, but now we know there is an extended version which will be present later. But when we were doing this, we didn't know that for non-invertible operators whether the Williamson normal form will work. So the class we considered is this. Yeah, I will explain the class. So what we did is that we consider a positive invertible operator T such that it's a translation of the compact operators. Compact operator, the spectrum will be clustering at 0. So I just shift it to some positive number alpha. That is the idea. Okay. So first we reformulate, as I mentioned, I need to reformulate, it's free of dimension, the inequalities. So what we did is, yeah, so this is something I mentioned. This class will contain the Gaussian covariance operators. Okay. So the class where we are going to prove this. So this is the reformulation. See, this is my, these are the inequalities. I am just listing down the inequalities on the final dimensional setting. Okay. So in the increasing thing, this is the inequalities. First eigenvalue, less than or equal to the first symplectic eigenvalue, and here the n plus 1 eigenvalue. So what do you do? Instead of, so now you just consider the first set of inequalities, this one. The first set of inequalities will tell you that in the increasing order, if you arrange, lambda j increasing is less than or equal to dj. Okay? So there no dimension will come if you are, dimension, it will be free of dimension. So simply write lambda j less than equal to j for every j. Okay. Now, the second set of eigenvalues you can actually reformulate by arranging it in the decreasing order. So if you change the order of writing it, then that will become like this. So this is a different order. You write the largest eigenvalue first and downwards. So that is why this downward arrow. So this set of inequalities are equivalent to these two inequalities. Two sets of inequalities. So now it is free of dimension. Okay? Now the question is, can we obtain this for some class of operators? So this is the class we consider. So T is a positive operator such that it is translation of some compact operator. So just translate it. So the set of such operator will be like this. See, if it is a compact operator, it will cluster at 0. But it's a translation, so we just shift it to alpha. So it can at most cluster at alpha, and all other will be countably many eigenvalues other than alpha. Alpha will be the only possible accumulation point. Okay. So now spectrum is fine. Now the challenge is that whether the same thing will be holding for symbolic spectrum. So that is not straightforward. So what we do, here the thing is that now with respect to alpha, right hand side also you will have eigenvalues and left hand side also we will have eigenvalues. So you need a kind of order, right? So you cannot get a single order. So what we do is that we denote the eigenvalues on the right with this notation R, and we arrange them in the decreasing order, and the left with this L, and we arrange from the increasing order. So the thing is that it can at most cluster at alpha in this from both directions. Okay. Now the point is about symbolic spectrum. So spectrum, anyway, there are eigenvalues with these ideas. Okay. Now symbolic spectrum, so this is a slightly non-trivial. You need to use some a little bit algebra thing, so that you will get that symbolic spectrum is also at most countable, and alpha is the only possible accumulation point. Okay, and this is what we observed. Then, so that you can again order this DJs here, and the symbolic eigenvalues also you can order like increasing from the left and decreasing from the right of alpha. Okay. Now another problem of this is on the right you have eigenvalues as well as symbolic eigenvalues. So now the point is that it is possible that right hand side you have only finitely many eigenvalues. So is that true that the right hand side symbolic eigenvalues also at most finite? So what you have to do is that you need to count the number of eigenvalues on the right and symbolic eigenvalues on the right, and same thing you need to do the left, and you need to show that if the number of symbolic eigenvalues is at most the number of the eigenvalues. So this is also something we observed. Actually we could prove this also, but that proof is slightly non-trivial, which makes use of some approximation, that you truncate it and approximation. So that is not real, so I will not present the proof. So the different cases may arise. So the cases means eigenvalues are finitely many on the right hand side or infinitely many, and left hand side like that. So considering all these cases, we proved the result. So so this is the result. So this is something with T2 and Mary. So so what we obtained is that, so this two set of inequalities are holding. So if you consider the right hand side eigenvalues and the symbolic eigenvalues in the decreasing order, so this inequality will hold for j equal to 1 to SR. Here what is SR? SR is the number of symbolic eigenvalues on the right, okay, which can be infinity also. But in a lemma we already proved that this is at most the number of eigenvalues on the right. Okay, so this will happen for everything. Okay, because if there are finitely many symbolic eigenvalues, it will happen for up to SR, and after that all the eigenvalues are about this. So the same thing happened on the left hand side. So this is the infinite dimensional analog of Bhatia and the. Okay. So this is one type of problem which I consider. A generalization of what we did in the finite dimensional. So what was there in the finite dimension to infinite dimension. So one more thing, I want to mention this. Yeah. So this result is applicable to the Gaussian covariance operators. I will define Gaussian covariance operator in international setting later. I will explain that. And also it is applicable to every class of operators known as absolutely norm-attaining operators. Positive absolutely norm-attaining operators. The point is that Paulson and of course Dept also contributed. So they obtained a kind of characterization result for positive absolutely norm-attaining operators. So which will tell you that will lie in this class. Okay. So this is applicable to these two things. Now let me present the approximation result of the symplectic spectrum. So here the question is, you have an infinite-dimensional positive operator where you can talk about symplectic spectrum. So you truncate it, I'll explain the truncation, so that you approximate this operator by finite dimensional operators. Okay. Now the finite dimensional thing, you can compute symplectic eigenvalues using some algorithms and all. So you will have a sequence of symplectic eigenvalues. As n becomes larger and larger, the operator comes closer and closer to the original operator. So whether the symplectic eigenvalues will approximate. So that is a problem. See, we were considering the problem for operators. So now, we were considering for the operator problem for spectrum of Stanford operators. Now here it is for the symplectic spectrum. Yeah. So here it is not general. So we consider two classes. So these are the two classes of operators we consider. One is operators of the form AB, where A and B are commuting separately operator from H. And of course, we are considering operators of H direct sum H. So you need to confine to our attention to these two classes of operators. Here A and B are commuting separately operators, and A, B, B, A or A. So these are the two classes where the results are true. Now let me explain this truncation method. So the idea is that you consider a complex separable Hilbert space and an orthogonal basis to that. And so you treat the infinite-dimensional self-adjoint operator as an infinite matrix. Okay? Like this. So suppose you have an infinite matrix, AIG. Okay? So you just look at the n by n corner. First n by n corner. So this is what you call AN. So this AN will converge to A in the strong operator topology. So, and you can actually write it as Pn A Pn. This is what your AN actually. Where Pn is the projection onto the first span of the first n elements in the orthogonal basis. Okay. So this is a finite dimensional operator, so that you can write as the n by n column like this. So the original operator you treat as an infinite matrix, and this is n by n column. Okay. Now the question is whether, so you consider the eigenvalues of this AN, sequence of eigenvalues, then you form two sets. So this set is the set of all complex numbers which are limit of some sequence from here. I mean, you collect the sequence of eigenvalues of AN and look at the limits and collect all those limits. That is what this limit infimum of sigma n. And if you allow some partial limits also there, then you call it limit supreme of n. So these are the two sets. And what is, okay, so just let me define what is an essential spectrum. Essential spectrum of an operator is simply a spectrum in the Kalkin algebra. You treat A as an element in dh by kh, or spectrum, which, the part of spectrum which is invariant under any compact motivation. That's what, yeah. No, now we are in the infinite dimension. Yeah, AN is a finite dimension. Yeah. What? Sorry. Yeah, it should be lambda. Sorry. Each lambda n should be. Yeah, I understood your problem. This is notation issue. So it means each lambda n is in AN. Not the thing. Sorry. Yeah. Is that your problem? I mean, yeah, the sequence with each lambda n in AN. Okay. Not like very. So this is not a problem. Sorry. Yeah. Thanks. So yeah, essential spectrum means the part of spectrum which is invariant under compact perturbation. Okay. In the case of self-adjoint operators, this will be set of all spectral values which are not Yeah, this may not be, some subsequent, this will be actually n tuples, and n will be increasing. So you can take lambda 1 in A1, and that you don't have to remind. Only subsequence will be there. Some n's can be missed. So you form an infinite sequence and take a partial limit means subsequence convergence. So in the separated case, these are speckle values which are not discrete eigenvalues of finite multiplicity. Okay, so what Bocher, Chitra and Nambudiri proved in 2001, that, first you look at the picture. So in the self-adjoint case, the spectrum of operator will be in this small m and capital M. It is a bounded thing. And essential spectrum will be between nu and mu. And I don't claim that all the values here are part of essential spectrum. There can be gaps. Okay? But outside this will be at most countable. And here also, above the bound, this will be at most countable. So this is a picture of the spectrum of a bounded self-adjoint operator. So when A is bounded and self-adjoint, then what happens? These bounds are already speckle values, and that will be subset of limit in set, that means the limiting set which we just considered. And this is here, and this limiting set will be subset of this whole closed interval. So taking the truncation and limiting, you will not go beyond this interval, but you will be, so this is called spectral pollution, when you will be computing something which is not a spectral value also. That's also possible. Okay? So, and when essential spectrum is connected, suppose this interval is fully part of essential spectrum, then what happens is that this coincides exactly with the spectrum of A. So you will not find, there will not be any spectral pollution. You can actually compute all the values outside this and the upper and lower bound of the spectrum. So if you have an additional information that essential spectrum is connected, then you can actually do this technique completely. Okay? So this is what they proved. And what we did is that we just invoked this result with the symbolic spectral theory. So that is our result. So how much time I have? 9 minutes. Okay. So let me just state this result. So in both of these class of operators, when T is AB, you can actually see that similarly spectrum of T is the spectrum of this thing. And when this is connected, essential spectrum of this is connected, you can actually perform this truncation method. And the same thing holds for this thing, this kind of operators. When the essential spectrum of this operator is connected, then you can perform the truncation method. So this is published in Journal of Math Physics last year. So now, one more thing proved here is this. So this is very important. If an operator is in this class A or class B, all the symbolic spectral values of T will lie in M. That means, see, later we have seen that, so spectrum will lie between this M and that something we know. And in fact, for any operator, symbolic spectrum will, so without any further assumption, that's the thing. You don't have to assume connectedness or anything. Symbolic spectrum will also lie here, within this bound. So that is also one information. So this will give you kind of bound estimate. So now here, as I promised, I will introduce GCO. This is a quotient Gaussian operator. Actually, how does it define like this? I'm not sure, but deduce this is the case that this will, Gaussian covariance operator can be this. It is equivalent to say that these three conditions. So one more thing. Whenever I say this, this is for the complexification of these operators, some technical terms. So an operator is called Gaussian covariance if these three conditions are satisfied. Okay. Now, for such operators, the symbolic spectrum will lie above 1, and it can cluster at most at 1. So there I can apply the truncation method directly, that all the eigenvalues on the above 1, you arrange them in the decreasing order, and it is possible that there are only finitely many, or it can be infinite. So you distinguish the two cases. if there are infinitely many eigenvalues, then the kth eigenvalue, so kth symplectic eigenvalue can be approximated like this. And otherwise, if there are this finite, then this will become 1. I mean, 1 is the cluster point, right? So this way, so it tells you that you can actually approximate the symplectic spectrum of a Gaussian covariant operators using the truncation method. So that is the conclusion. Yeah, it can be completely. Now let me mention 3 problems. So this problem actually recently Hemant Kumar Mishra extended the Williamson normal form to what you call real symmetric matrices. That means the operator and the matrix need not be positive and invertible. So there is an extension to it. So now the question is, here's see, the symplectic, the Williamson normal form is a kind of speckle theorem. I mean, it's like speckle theorem. So in the bidimensional case, you have speckle theorem for symmetric matrices. Okay. So now the question is, infinite dimensional case. So can you have a symplectic speckle theorem? So that means, can you represent the operator using the spectrum? So like in the compact self-adjoint case, you can represent the operator using the eigenvalues of the compact self-adjoint operator. And in the bounded self-adjoint case, you can represent it as an integral using the spectral measures and all. So do we have a kind of integral representation in the infinite dimensional case? In fact, we believe that this answer, we got a positive answer. So Anjali will present this today evening. So more or less we computed the things and all. So this is something we have some progress. The second problem, actually we don't have much progress. I just mentioned this problem. So this is the classical Seago distribution theorem. This tells you that you consider Topliss operator and consider this truncation. So just think that you have an infinite Topliss matrix and truncated Topliss matrix. So and you consider the eigenvalues of the truncated Topliss matrix. So then this quantity will converge to this thing, where F is the symbol which gives you the Topliss operator. So this is a kind of, I mean, you know that the measure concentrated on the eigenvalues will converge to something called density of states. Anyway, there is a symplectic element. Yeah. It is a very old paper, but this year is correct because it was published somewhere else, and they published. Yeah, it was in German also. I think in the original version was in German. So then, yeah. So now the question is, you have see. So they obtained a symplectic version of this. So while they did this, they produced some kind of block Topliss operators and so on. So in the proof technique and all, if we go through, there will be several problems arises because, you know, when we do the Seago distribution theorem, the corresponding what we have that there's a spectral inclusion theorem for block Topliss operators coming to picture. Similar, our question is similar symplectic spectral inclusion theorem for block Topliss operator. So this is more or less close to writing it. But the other two problems, this preconditioning and these things, so this I will not mention this problem because this is actually, you consider the system of infinite system of linear equations with Topliss structure can be replaced by what you call preconditioner of circular matrices. So can we do the similar thing here with using the instead of eigenvalue clustering, can we do it with symplectic eigenvalue clustering and all? I will not mention this because I did not mention the necessary tools here. But this is the final problem. Recently, Devendra, Tiju and Sumesh, they found an equivalence of quantum Gaussian channels where the finite mode Gaussian states plays a crucial role. So they answered a question posed by KRP 15. So recently this is published in Philosophica Transaction. So now what happens if you have infinite mode Gaussian states and if you have syllabus? Here we don't have any progress and we just stated this problem. So yeah, so this is what I mentioned. So thank you. The references. So this is where they obtained Williamson normal form in the infinite case, and this is Rajan Dept and Tanvi, where they obtained the inequalities, interlacing theorem. This is the ego distribution theorem due to Rajan Dept. This is the truncation result due to Bocher, Chipra and Yamadan, and this is the classical Zigo thing. And this is where Tiju ourselves we worked with this inequalities extension to the infinite dimensional thing, and this is where we obtained the approximation. These are the recent results by Mishra. This is where infinite mode Gaussian states were characterized by people, and this is the recent result due to Devendra, Tiju and all. And this is the classical paper by Williamson. Thank you.
Are there any questions?
Yeah, actually, this is only one particular result from Bhattia's paper. It's a big paper. It contains log ICOST. Then in another paper by Hemant Kumar, I think they consider Litsky's inequality, I think. So the symbolic version. Yeah. We didn't try, but they had. See, for trying the international thing, there are a lot of constraints coming to it. For example, log station you need to introduce it in a proper way and all. I mean, yeah, it is there in their article, but we didn't try. Yeah, that's something Anne-Marie almost, I mean, she will present it. So Mishra's paper is still in archive. So we obtained something when what we wanted. I mean, we actually, Mishra obtained the real symmetric operators version of the Williamson form. So what we obtained in infinite cases, we obtained that version, Williamson form. I mean, she will explain in detail. The question is, when does the Williamson normal form works? For positive operator, invertible operator, we know. What happens if it is positive but not invertible? Then there is a condition. Like the kernel should be a symplectic subspace and so on. So then the question is for arbitrary symmetric operators. So there also, under some conditions, this will work. So there is an equivalent condition. This one paper is also like that. There is a three set of conditions should be satisfied to get this Williamson normal form. So we obtained a similar thing. But what we obtained something more is that we actually obtained the integral representation of the operator. We believe so. It is yet to be published. We are just writing it down. So integral representation of the using the symbolic spectral machine. But here everything has to be defined in the infinite setting, which she will explain.
Question in the last session. Let us thank the speaker again.
Thank you.
Thank you, sir. I would like to invite